Problem number 7, we've got a circuit with a 120 volt battery. It's connected to a resistor, which is 5 times 10 to the 5 ohms, and a capacitor, which is 8 microfarads. The first question states that the switch is closed for a long time. Determine the charge on the capacitor when equilibrium is reached. So what happens here is that as the voltage goes through the circuit, it has maximum current. It'll travel through the resistor back to the charge, but along the way, it adds positive charges to the bottom plate, and that in turn will attract negative charges on the top plate. Now it'll continue this current until we've got a buildup of charge on my capacitor that is the full voltage of the battery. So the first question, determine the charge on the capacitor. The charge on the capacitor is Q, and we know that Q is equal to the capacitance times the voltage. That's 8 times 10 to the negative 6 farads times 120 volts, which equals 96 microcoulombs. So this is our answer for the charge on the capacitor. Once equilibrium is reached, we know that the charges can no longer pass, and because it's in series, our current is equal to 0. So we don't have any current going through the resistor, and if it were a light bulb, the light bulb would go out. The next step is to determine the energy stored in the capacitor. So you see, there's many equations, but 1/2 CV squared is one of them. I know that the capacitance is equal to 8 times 10 to the negative 6, and the voltage is 120 squared. So my capacitor, the energy in my capacitor is going to be 0.0576 joules. All right, the spacing between the plates is doubled, and it tells us after an extremely short time what's going to happen. So we're going to go back to our capacitance equation, where the capacitance is the dielectric constant times epsilon naught times area over distance. And we know that if the distance doubles, the capacitance is an inverse proportion. It is therefore going to decrease. So the original capacitor, or the new capacitor rather, let's put C new, is going to be double the original capacitor because of the inverse proportion. Sorry, not double, half C naught divided by 2. Okay. After a short time, we need to think about how my circuit is going to react. So our equation here is charge over voltage. In a short period of time, no charges have moved yet. And therefore, if the capacitance decreases, the voltage has to increase. They are inverse proportions. So V new is equal to double the original voltage. Now, what does that give us? My new voltage here is not 120, but it is 240 volts. So what we are determining the work. Work is equal to change in energy. So first thing we want to do is figure out what our new energy equation. U new is 1/2 CV squared. 1/2, the new capacitance is C naught over 2, and the voltage is 2 times V naught squared. If I simplify all of this down, my 2 squared gives me 4. That reduces down with this 2 in the denominator, and I end up with 2 times my original equation, 1/2 C naught V naught squared. So if I look back at the original and I solve for that, I really have my new energy as double the original. But we are asked for the work done or the change in energy. So work is going to be the new energy minus the old energy, which is equal to 2 U naught minus U naught, and the work is therefore just U naught. And our original U for the capacitor was 0.0576 joules. Okay. Next up, we need to determine the current in the circuit immediately after the increase in spacing. So let's go back up to our scenario. And I'm going to clear out some of these current values. And I know that I built up some positive and negative charges here, but now that we've separated the capacitor, I've increased the voltage. The voltage has built up double the positive charge on the bottom, which means I'm going to have current wanting to go this way. I've got a 120 volts wanting to go this way, so my net voltage is going to be, if my 240 is going counterclockwise, and I can call that negative 240 volts, but I'm counteracting that with a positive 120 volts from my battery, I end up with, and let me show you, the net current is going to go in this direction and back to the capacitor. The reason why is because I've got a much larger voltage on my capacitor, actually double the voltage of my capacitor than my battery. So it's gonna overpower that current. What I end up having is a negative 120 volts going to the, what direction is that? Counterclockwise. 120 volts in this direction, which is counter. Okay, so now we know that the current is going counterclockwise. In total, after it's being counteracted by the 120 volt battery, we've got 120 volts going counterclockwise. So what we need to do is solve for current. Current is equal to voltage over, and this is the net voltage, over the resistance. My resistance still stays the same, so I'm going to take my 120 volts divided by my 5 times 10 to the 5th ohm resistor, and I get 2.4 times 10 to the negative 4 amps counterclockwise. This is immediately after. So this is the maximum current. Once the capacitor starts discharging, that current is going to decrease, obviously, but we can calculate the maximum by using the Ohm's law equation. Okay, so let's get into after a long period of time. The current stops. An equilibrium is reached. So we want to figure out what the total charge is through the battery. What we do know is that after the capacitor has increased distance, the net voltage, this is for part E, the net voltage is equal to 120 volts. We also know that our equation for charge is equal to voltage times capacitance. So we want the charge that passes through the battery. The battery pushed charges going to the left, but in total, the 240 volts is going to push more charge through the battery, and that is going to be relative to the difference between the 240 voltage minus the 120 from the battery. So we end up with 120 volts. That's the net voltage going counterclockwise times the capacitor, or the capacitance, which is 8 times 10 to the negative 6. And that gives us, one thing I forgot to emphasize is after the change, my capacitance decreased. So really, I have to decrease this by 2. My equation here, it's still 120 volts because that's what goes through the battery, but I really have to take 120 times 4 times 10 to the negative 6. In the end, that gives me 4.8 times 10 to the negative 4 power, and that is a charge in coulombs. Okay, last but not least, let me erase this. I have part F, the amount of energy added to the battery. Again, UC is going to be, when we're talking about added, the extra voltage. So that's going to be 1/2 CV squared. The capacitance, again, is going to be half of the original capacitor. So that's going to be 4 times 10 to the negative 6. And then the voltage is going to be the net voltage, which is the 120 that's going counterclockwise through the battery squared. And then this leaves us with 0.0288 joules.